In this video, we're going to be talking about formal charge and resonance. Now, we've looked at Lewis dot diagrams, we've looked at Vesper diagrams, but there's one type of covalent bond that we haven't examined yet. Do you remember when we looked at ionic molecules and we had these polyatomic anions like the phosphate ion, PO4 3-, or the sulfate, SO4 2-, or let's do two more examples. NO3-, that'd be nitrate, and let's go carbonate as well. CO3 2-. How do these get modeled? Well, let's start by looking at the PO4, the phosphate. Let's make a Lewis dot diagram out of that. So I'm just going to set that up here. Okay, so if I count up all of my electrons here, I've got a total of 29 electrons. And so let's draw out that molecule, doing our rough draft. Phosphorus connected to oxygens. And then I've used 2, 4, 6, 8. So I'm going to take 8 away, and I'm left with 21. And if you can look ahead, you might see that this isn't going to work. If I put all of these around, okay, now I've used all 21 electrons, and I'm missing 3. But you might have noticed. You might have already noticed this. This has 3-. That means it has 3 extra electrons that we haven't accounted for. Let's keep those in blue. Let's keep those in a different color. So I've got 3 extra electrons here that are just hanging out because this is an anion. It took those electrons from somebody. You know, maybe some poor sodium atom was whatever. So now I've got those 3 extra electrons, and this looks to be complete. It looks like this is a completed Lewis dot structure. This seems fine, right? But remember, oxygen would prefer to be making 2 bonds, right? So we've got this structure where oxygen is making only 1 bond when it would rather be making 2. I mean, all of our numbers check out. Everything has a full octet, and everything has. I've used all of the electrons available. So is there an issue with this? Remember phosphorus too. Phosphorus would rather be making 3 bonds. So what are the consequences of these atoms having to go outside of these norms? Well, there is a consequence, and it comes in the form of something called formal charge. Each of these atoms is going to have a charge other than 0. They're not going to be neutral. And in a covalent bond, that can pose a problem. So let's look at how we calculate formal charge. Formal charge is going to be a quality of each individual atom. And we calculate it using this equation. So Fc stands for formal charge. V equals the valence electrons that it starts with. N is going to be the number of non-bonding electrons. And B is going to be the number of bonds. And so if I use oxygen here, this oxygen right here, if I use that as my example, let's use some different colors here just to help us keep track of things. Let's use this oxygen. Well, it's going to start with 6 valence electrons minus number of non-bonding electrons. It's 1, 2, 3, 4, 5, 6. It's going to be 6 here. And number of bonds, it's got 1 bond. So it's got a formal charge, 6 minus 6 plus 1, of -1. So this oxygen right here has a formal charge of -1. Are these other oxygens different? How about this one? How about this one right here? Well, that also would have 6 valence electrons. It also has 6 non-bonding electrons plus 1 bond. So that also has a -1 bond. So oxygen, anytime oxygen has just 1 bond, it's going to have a formal charge of -1. How about this phosphorus? What is that one going to have? You might be able to calculate this on your own. In fact, you probably should. So let's take our valence electrons here. That would be 5. It started out with 5 valence electrons minus the number of non-bonding electrons. So that's 0. Plus the number of bonds. Well, it's got 4 bonds. 5 minus 4 is +1. So this phosphorus has a +1. Now, hopefully you can already see where we're going with this. These charges are going to be attracted to each other. This -1 is going to be attracted to that +1 by Coulomb's law, right? Told you this was going to come in handy. It's going to come up a lot. So Coulomb's law is going to say that the electrons here are going to want to move over towards this phosphorus. And so we're going to see that occur. All right, so I've redrawn the phosphate. with a double bond on one of these oxygens. And that's to show that this negative charge here caused an electron pair to bond to the phosphorus. So that's going to be this molecule's solution to try and alleviate that formal charge, that difference in charges. And so now if we look at this, oxygen, its formal charge, so this oxygen, we're looking at that one right there, its formal charge, it started with 6 valence electrons. It's currently got 4 unbonded electrons and 2 bonds, and so its formal charge is 0. Excellent. And how about this phosphate? Well, that phosphate, it would have 5 valence electrons minus 0 unbonded and 5 bonds. So its formal charge is 0. Okay, great. So this oxygen and this phosphate are now neutral. So they're going to be a lot more stable that way. But these 3 oxygens, those are still going to carry that -1 formal charge. All 3 of them. All 3 of them have that charge. And so we can kind of see that's where this charge on the phosphate anion is really coming from. So if these all have a negative charge, what's going to stop the electrons here from trying to flow towards this new area of less negative charge? It's not really positive, but this area right here, this area is less negative. And so these electrons, these charges, those are all going to want to flow towards that area. And so what's going to happen is I'm going to have a steady flow of these electrons all moving and trading places, and this extra double bond right here is going to be flowing around this phosphorus. And so I could draw this a few different ways. Okay, so now I've got 3 of the same molecule drawn, and I can see that this extra bond, this bond right here, keeps moving around. First, it's moving up here to try and alleviate the negative charge on this oxygen. So it's sitting right there now. And then it's going to move down here to try and alleviate that charge. And now we can consider, how quickly do you think this bond, this electron pair, is going to be moving around this atom? Well, it's going to be moving so fast that we can't really differentiate which bonds have that double bond and which ones don't. And so when we have a situation like this, where we could have this double bond on any of these molecules, we can actually say it's really being shared between all 4 of these oxygens. And so instead of having a single or a double bond, we get this thing that we kind of call a 1.5 bond. And so we designate that by doing a dotted line on each of these bonds. And we call this total structure, this composite structure, this is really a mixture of all of the different combinations we could have. We call this a resonance structure. And we say that these bonds are resonating with each other. So they are trading an extra electron back and forth between them all the way around. And so that negative charge gets shared between all 4 of these oxygens. And so if we were to calculate our formal charge again, we would see that it's about -3/4 for each oxygen. So that the total thing, the whole phosphate, has a total charge of -3. Now, when we draw out resonance structures, and we will be practicing this, we will be drawing some of these. When we draw these out, we don't put any valence electrons around the oxygens, just because all of them are kind of sharing that double bond. So there's not really a good way to say how many electrons it would have around it. Now, you might see some instructors say, yes, draw the electrons around it. I never require that because it's just kind of a hassle. So let's see what this looks like with another molecule. Let's try sulfate. Okay, we have a completed Lewis dot structure here for sulfate. And now let's go through and let's calculate our formal charge. Now, Fortunately, these are all oxygens, so we can already tell that all of these are going to have a -1 charge because we already have experience with that. We have the oxygen where it's got one bond. They're all going to have that -1 charge. But what is that sulfate going to have? What is sulfate going to have? Well, sulfate started with 6 valence electrons. It's currently making 0 bonds, and it's got 0 unbonded electrons, and it's got 4 bonds. So that's going to be a +2 formal charge. So if that's a +2, that's able to cancel out 2 of these -1s. Okay? So we can see that's where that -2 is coming from for the overall ionic charge. But when that tries to resonate, it's going to form 2 double bonds. And so whenever we're drawing resonance structures, we need to draw at least 2 of our composite structures to show that a resonance structure is valid. Okay? So we can see that we have at least two possible structures here. We could draw these double bonds all around this sulfate atom, and we can see that because they're all oxygens around it, it's not really going to make a difference. Any of them could carry that double bond. And so we've successfully shown that we could have a composite structure, or a resonance structure here. And so now we draw a double bond, or a double arrow, to a resonance structure. We're going to draw this by first drawing out the single bonds. We're going to put a dotted line to show that all of these could have a double bond. Okay, so that's our completed resonance structure. And so I'm going to draw some brackets around this and put a 2 minus there. So that's how we would draw this if we're drawing out our anions. And so let's just talk about these 1.5 bonds real quick. When we as chemists work with molecules like this, we are actually able to, there's really sensitive measurement techniques that are able to measure the length of a bond. And we've measured the length of single bonds. We've measured the length of double bonds. But when we look at structures like the sulfate ion, we find that it's got these bond lengths are somewhere in between single and double bonds. And so we can tell that there is something unique about these bonds, that they are somewhere in between a single and a double bond. So in physical reality, this is the structure that we really have when we have the sulfate ion. It's not really sitting at one of these configurations. It is staying as this resonating sulfate anion. Okay, let's look at 2 more. Let's look at our carbonate, and then let's look at our nitrate, just so we have a full picture of this. And now in carbonate here, my carbon needs to make a double bond in order to have a full octet. And so before we even get to the resonating, we have a double bond. So now we can go through and calculate our formal charge on these. This oxygen, we can see that one's going to have a 0 for a formal charge. It's got 2 bonds, just like a normal oxygen would. These oxygens here are each going to have a -1 formal charge. And this carbon, let's look at that carbon. Well, it normally has 4 valence electrons, right? Minus 0 unbonded plus 4 bonds. So it's going to have a formal charge of 0. Great. So the only things with charge here are the oxygens. But this is still going to resonate because these areas of negative charge here want to move over here. And so I draw my double arrows, and I'm going to draw this in a different configuration. So here's another perfectly valid Lewis structure. So I can show that there are really 2 options for this configuration. And so I will have a resonance structure. So there's my proof for the resonance structure. So I need to make sure I draw my proof, and then I can draw my full resonating structure. To do that, once again, I start by just drawing the single bonds. Then I draw my dotted lines to show that this is somewhere between a single and a double bond. I'm going to draw my brackets around it. my 2 minus, and there we go. There's my resonance structure, all completed. Now let's do NO3. All right, I've used 18 electrons, so this nitrogen, this is going to need to make a double bond with one of these oxygens. And so if I calculate my formal charges here, this oxygen would be 0, these oxygens would be -1. What would this nitrogen be? Well, it's going to have 5 valence electrons to start with, and then it's got no pairs, and it's got 4 bonds. And so it's going to have a total charge, formal charge, of +1. So this nitrogen has a +1 formal charge. What that means is these electrons, those are going to want to flow to that nitrogen. They're going to want to make a double bond here. And so we're able to draw a resonance structure. Okay, and we can see that we have 2 perfectly valid structures, so we can draw out a full resonance. There we go. There's our resonance structure. For a moment, I want to come back to this sulfate anion. When we start to study acids and bases, we're going to talk about something called sulfuric acid. And sulfuric acid is just this sulfate anion attached to 2 H+ cations. And what that looks like, when that happens, these H+, where could those bond? Well, the most stable configuration would be for those to bond right here to these oxygens. So I could grab a bond with an H right here. And if I do that, we can see that suddenly this oxygen has 2 bonds now. Its formal charge just dropped down to 0. So this has a formal charge of 0, that has a formal charge of 0, and these both have a formal charge of 0. This sulfur right here, well, that's going to have 1, 2, 3, 4, 5, 6 bonds. 6 valence electrons minus 0 unbonded plus 6 bonds. That means that has a formal charge of 0. And so when this sulfate is connected to these hydrogens, that's going to lock this resonance in place. But once that enters into water, and we're going to see that something like this acid, it's going to protonate, which means it's going to lose one of these hydrogens. One of these hydrogens would go away. Once that happens, suddenly, this oxygen has a formal charge of -1, and these 3 are going to start resonating with each other, spreading out that negative charge. So we're going to see that, okay? So what we should walk away from this with is that we can calculate the formal charge of each atom in a resonance structure. We can draw molecules, perfectly valid Lewis structures that have formal charges to prove that a structure will be resonating, and then we can draw the composite resonance structure.